In this video, we're going to look at one of the key skills that we have to develop in our work with functions at higher level mathematics. That is the skill of graph transformations. Now, when we were doing National 5 Maths, we looked at some basic graph transformations when we had trig curves. So when we had y equals sine, cos, or tan x. We looked at some generic versions of transforming each of those using y equals a sine of bx plus c, y equals a cos bx plus c, and y equals tan bx plus c. We looked at how they change, and it was quite nice because those are periodic functions. The behaviour repeats over and over again, so the changes were quite easy to manipulate and observe. However, what we're going to do now is take this a step further. We're going to take it and actually apply it to generic functions that don't have a periodic repetition like the trig curves do. Now, when we're doing these, there are 6 key transformations we have to be able to work with, we have to be able to manipulate, and we have to be able to understand. And these are them. Now, all 6 of these come from our big generic functional form that we want, y equals a f of bx plus c plus d. Now, this is what we get when we combine them all together, something we'll look at in our next video. But first, we have to understand what each of these does. Now, this first one here, y equals a f of x, think of that in terms of your y equals 2 sine x, or y equals a half cos x. Think what that did to the curve. What that did was it took the curve and it stretched it or squashed it in y. And that is the exact same behaviour it does here. So it either stretches or it squashes in y. Yeah, so it changes the magnitude of the curve. Now, in order to do that, we have to look at the size of a. Now, if the size of a is bigger than 1, so 2, 3, 4, even 1.1, it's going to take the curve and it's going to stretch it out. So it's going to make it bigger. If the size of a is somewhere between 0 and 1, so a half, a quarter, 0.2, it's going to squash it in y. Now, if we get negative values, that's going to come into play down here later on. We'll discuss that then. These are the key things we have to work there. Now, what happens then, an easy way to think of this is we take every coordinate in the graph and we manipulate it. Every coordinate that starts at our generic point x, y changes the same way with this. It changes and moves to the point x, comma, ay. So if I was at the point 2, 3 before and my value of a was 6, I would change the point to 2, comma, 3 times 6, so 2, comma, 18. It would stretch it up. This is how it works for anything, regardless of whether the size of a is bigger than 1 or between 1 and 0. Now for this one here, f of ax, where the a is with the x, again think of it in terms of the trig stuff, that stretched or squashed the curve again, but in this case, it was in the x direction. Alright, it's having an effect on the x part of it. It was in the x direction of the curve. And this one, unlike the y, actually went against the grain. So to stretch it, this time it actually stretched if the size of a was between 1 and 0. And it squashed it if the size of a was bigger than 1 in this case. So it was kind of the opposite effect. Alright, it did the opposite to what we wanted it to when it was in the x direction. Again, we could look at how it changed each of the points on their own. So if we again started at a generic curve x, y, our y part wouldn't change, doesn't have an effect on the y in this transformation, but in the x, it would move to the equivalent of 1 over a times whatever the value of x is. So if this was at the point 2, comma, 3, and a was 2, it would then be a half of 2, so 1, comma, 3, the y wouldn't move. This one here, y equals f of x plus a. Again, think back to our trig transformations. This sort of one here took the original curve and added something to it or took something away from it. It shifted it up or down. So it shifted up or down in y. And it shifted up or down by the value of a. Okay, and this took every point that was given at x, y, and moved it dependent on what that value of a was. X didn't change, it didn't move along at all. It was just in y, so we added a value of a onto every value of y. So if it was negative, we'd be taking away values, so we'd be shifting it down. If it was a positive value, we'd be shifting it up. again, this sort of transformation here, we're adding something to the x's, so we're looking at another value of x that we already have for the curve. So again, it's shifting it based on that, but instead of up or down, it's left or right in x. And this is where the difference comes in though. It's shifting it by a value of negative a. So any generic point we've got that starts at x, y, shifts to the coordinate x minus a, comma y. So if this was f of x plus 3, everything would move down 3, so you'd be taking away 3. Again, x does the opposite to what we want, and x does the opposite to what we think is going to happen. This one here, y equals negative f of x. Well, simple way of looking at this is every value of y is negated. That's what it wants, so this is just a reflection. This one here reflects in the x-axis, i.e. it just flips the curve over. Again, look at the points. If I'm at a point x, comma y, that one simply shifts to x, comma negative y. And this one here, y equals f of negative x, well, it's the x that's being flipped in this one. It's the x with the values negating. This one here reflects in the y-axis. Alright, this one reflects in the y-axis. So I take my point x, comma y. Nothing's going to happen to the y element this time. It's my x that's going to be flipped. So it's going to go to negative x, comma y. Each of these transformations is vital that we understand how to do it. And it's vital that we can do it fairly quickly off the top of our heads. What we're going to look at now is I'm going to show you an example of doing each of these on their own. And then there's a second video after this where we're going to look at an example or two where we're combining several different transformations together. So imagine I now give you just a generic little curve. I'm going to say it's just a curve that looks something like this. Goes up here, cuts the no-axis to there, and goes to there. So again, this is just for a general, generic curve. And I'm going to say it's at the point negative 1, comma 6 here. And this turning point down here, I'm going to say is at 4, comma negative 1. I could perform every single one of the transformations on this graph just to see exactly how it works. So imagine I had y equals 2f of x. So imagine I wanted the transformation of that. Y equals 2f of x. Well, I know that 2f of x grabs the curve and it stretches it out. It doubles all of the y values in this curve. So essentially, I could imagine taking my curve. It's not going to change the general shape of it. So it's still going to look something like that. But what's going to happen is the y parts of my coordinates, especially my turning points, are going to stretch. And these are the ones we have to mark on. We have to mark on every key point we're able to understand and know for the curve. So this one here, the x stays the same, it would be negative 1. My y would stretch up to 12. This one here, my x stays the same again. This now stretches down to negative 2. Imagine I then said to you, right, I wanted to do the same, but this time it's going to be f of 2x. This time I'm going to take it in to the x part. So I'm going to say f of 2x. Well, again, this is the one that stretches or squashes it in x. Now think of it as being the opposite. So we said if the number is bigger than 1 in the y direction, it stretches it, but x is the opposite. So in this case, it's actually going to squash it in the x direction. So again, the generic shape of the curve stays the exact same, so it still looks something like that. Our y coordinates are still going to stay the same from the original curve, so it's still going to be at negative 1 there. But my x coordinates, because it's 2x, are going to be the same as 1 over a times the x, so they're going to half. So I'm going to end up at 2 comma negative 1, and this one here is going to end up at negative a half, comma 6. The y doesn't change at all in that one. Imagine, for the first one, instead of 2x, 2f of x, I said a half, f of x. So imagine I took it and multiplied it by a half. So in this case, what would happen to my curve is instead of stretching it in y, I squash it down. So I'd squash my heights down in y in this case. Again, same generic curve, same generic shape. All that would happen is my y coordinates would change. So my negative 1 would still stay the same. This would go from 6, it would become half. So it would go down to 3. this one here, x would stay the same at 4. It would then squash up in y and go to -1/2. If I did the same sort of transformation this time in the x direction, so y equals f of 1/2 x, well, again, I'd think to myself, right, in y that would squash it. However, x does the opposite, so the 1/2 x would stretch it in the x, so it would actually double the x portion of each of the turning points that we've got there. So the graph would again still be the same generic shape, except this one would now no longer be at 4, -1. It would double out, so it would be 8, -1. This one here would double out again and be at -2, 6. This is the way the transformations can work in these cases. And we can actually look at the other ones the same as well. So again, let me just quickly sketch the generic curve that we're using. So we've got our little curve that goes up like that, down there. I've got the point 4, -1 there. And I've got my point -1, 6 here. Imagine I wanted to do the transformation y equals f of x plus 1 like that. And underneath it I'll do y equals f of x plus 1, but the plus 1 is with the x this time. So imagine I wanted to do each of those. Well, this one here I know is going to shift everything up 1. It's not going to harm the x's anyway, it's not going to touch them, it's the y's it affects. So the curve will go up like that, and down. Now this is where you have to pay attention. This one here goes at 4, -1. If it shifts up 1, this no longer is a curve below the axis, it actually moves up to a turning point on the axis. So this is where we have to start making sure that we're taking these things into account, because now that point there is on the x-axis. This one here goes from -1,6 to -1,7. Now this one here, f of x plus 1, again it goes against the grain. You would think you're adding 1 to it, so it's going to go up, but no. We're adding 1 to it, so it's going to go left. It's going to go essentially down in x. Curve is still going to stay the same. It's going to be like that. At x values, this one here was at 4, -1, goes down to 3, -1. This one here is at -1, 6, it goes down to -2, 6. So these transformations follow this pattern as well. As for the other ones, y equals -f of x, again you flip it in the x-axis, exactly like I said. So we rotate the whole curve round, so essentially this one then just goes and becomes like this. And we flip the y values, so my turning point that was there would go to -1, -6. This one here would go to 4, 1. And if I did the exact same with a negative affecting the f, so it would be f of -x, my whole curve again would reflect, but this time it reflects in the y-axis, so it rotates itself around. So this one would now go on to become something like this. This point, which was 4, -1, becomes -4, -1. And this point here, that was -1, 6, goes and becomes 1, 6. This is how it affects them all. These are the key things we have to remember. Whenever we're doing graph transformations, these are the key rules that we have to be able to follow and have to remember. And if you want a bit more practice at this, look at the next video where I'm going to show you several different ways of transforming curves, but also bringing in several different transformations all together.